happy to have Elena D'Onghia visiting from University of Wisconsin, and she's going to talk about structure and dynamics of the Milky Way stellar disk.
Thank you very much for this invitation. I'm very happy to be here. I know that everyone is very excited about gravitational waves this week, but let me tell you why Milky Way is very exciting these days. So let me tell you first, why I think it's so important to study the Milky Way. First of all, 50% of the stars in the 2 days universe are locked in galaxies with the same mass, size, and chemical abundances as the Milky Way. So very common type of galaxies around us. Also, the Milky Way is the only galaxies for which we will have information about three-dimensional information about the space, and the phase space velocity, positions. We will have chemical abundances. So we will be able, with Gaia, with a survey which is already started, and complementary to the SLOAM 4, with Apogee, we will be able, in these years, to have also information about stellar ages. So this is actually the decade of the Milky Way, thanks to the surveys, but we need also modeling. We need to be able to model everything we observe. So we will be able to have a three-dimensional map of the Milky Way for 1 billion of stars in the stellar disk. Also, why these data are so interesting right now? But because they will tell us a lot of things. First of all, we can learn about how these galaxies do form and do evolve. The Milky Way is a very common galaxy, as I said, in the nearby universe. We can learn about the formation and evolution of these galaxies. We can also learn a lot about the gravitational potential of our galaxy. We can learn a lot about different contributions between stars in the disk, dark matter distribution, so we can learn a lot even locally and for the entire disk, how the dark matter contributes to the total budget mass of the Milky Way as a function of radius. Also, why focusing, in the title you've seen, why focusing on the stellar disk of the Milky Way? I think the stellar disk of the Milky Way is very prominent in our galaxy. So it's three-fourths of the total stars of the Milky Way are actually in the disk. And compared to the other galaxies, if we look at other galaxies for which the Milky Way is very similar to, the Milky Way has a very prominent stellar disk as compared to normal L-star galaxies. It doesn't have a prominent bulge, but or it has a bar, but it's not so prominent. But the stellar disk is a huge component. So, which are the relevant questions I'm trying to answer? And I'm showing you actually the research I've been doing in the last few years. So first of all, I think it's still not clear how do galaxies like our Milky Way form spiral structure. This is a very old problem. It's a problem that's been for mathematicians, physicists, astronomers right now. Still unsolved. I think we don't have a consensus, or exactly we don't know what's the origin of the spiral structure is. Also, very interesting, disks, stellar disks get hot, they heat it up. How this process happens? What determines the radial and the vertical structure of a disk? So for example, which is the role? So is there a role from an internal process, for example, that moves the stars in the disk at different radii? For example, the presence of the spiral structure actually exerts some torques on the stars in the stellar disk, and stars that can move from their initial origin. It might be possible that our sun is an immigrant in this part of a galaxy. So radial migration, which is this process that happens inside stellar disks, due to torques, essentially from non-asymmetric features like a bar or spiral arms, creates a lot of migration of stars. And they want to figure out which is, to assess which is the role of radial migration in redistributing or even affecting the stellar structure of the disk. Also, our Milky Way, if you think in a cosmological context, it is embedded in a dark halo, and these days we are able to do cosmological simulations in the most popular scenario for structure formation, which is the lambda CDM model, the cold dark matter theory. Simulations are very, they can make very clear predictions right now. How many satellites are expected? How many dark clumps of dark matter are expected to be around the Milky Way? I can tell you within 500 kiloparsec, we are expecting at least 500 satellites with different mass and size. What do these satellites do to the stellar disk? Do they bombard the disk? Do they pass through the disk? How many of them, is passing through the disk? And how this external perturbation actually can affect the stellar disk and the vertical structure of the disk. So more generally, I think the big question is how resilient are stellar disks to tidal interaction with satellites or, in principle, with anything can be predicted in the lambda CDM. Just to tell you the truth, probably you already know that we have visible satellites around our Milky Way. For example, Sagittarius, a dwarf galaxy. We know that it punched the disk almost a giga-year ago. So it's important and interesting to figure out what is the effect of a satellite on the, which is the role on the disk.
So my question about that is, for some of these infalling satellites, we have lots of data in terms of where we actually see the streams. And of course, flow and so forth
sure.
Very important. But are you talking also now about indirectly constraining some kind of very low surface brightness kind of streams just from the fact that it had impact on the stars that we do see in the stellar disk?
I will look at more for this talk. Actually, I'm focusing more on the response of the disk, the dynamical response of the disk to a perturbation of a satellite infalling. But my research also touches streams. The streams around the satellites on the sky, just not focusing in this talk. For example, we have the Magellanic stream, which I'm actually working on right now. We have Sagittarius as a stream of stars. So right now I'm not actually focusing on that. Although some, with Gaia, we will be able also to assess some of the properties for the nearby streams. So I will talk about streams, but not the streams attached to satellites. I will talk more about substructures inside the disk right now and the response of the disk to perturbations. Okay, let me tell you what I've done recently in the last few years about the spiral structure. As I said, this is, I think, still a fundamental problem. It's a fundamental problem because after more than 50 years of theoretical studies, I don't think we have a consensus in, what generates spiral arms and what these spiral arms are, and essentially which are their properties. So if you look at around our Milky Way, 70% of galaxies are disk galaxies. So disks are, you require disks to have spiral arms. But if you look at, these spiral arms are these prominent features here. So if you go from M51, which is one of the most famous galaxies studied, you can see that there are two arms, two very prominent arms. But now let's move to M74. You can see here that the number of arms changes, the amplitude probably too. They have a different shape. And if you go to NGC 7217, it's almost it's hard to enumerate the number of arms here. So these are called kind of a flocculent galaxies. They have, it's very hard to see how many arms there are there. But still, it's plenty of features. So what determines, I think the big questions are, what they are, how are they generated, and how can we regulate the number of arms? How can we understand, how many arms galaxies do have? So let me just tell you quickly about the leading theories that, from the 60s. These are theories that have done, it's all analytic work, all linear theories. Maybe, the most famous leading theory was the one from Li and Xu. It's the one usually on books. So, in this theory, spiral arms are density waves which are propagating through a disk, a differentially rotating disk of stars and gas, and they have the property that they are static. So these are global patterns that they do propagate without changing much by time. And there's no way in the theory to know exactly what is the source of this perturbation. But once they form, the gravitational interaction inside the disk, the gravity will not be able to change them according to the theory. Now, what is so interesting? Well, I would say the properties of these long-lived arms. So they are long-lived. So once they form, they never change, and so, they should be forever there. Of course, a nice part of this theory is that you don't know what is the initial source of perturbation, but you don't have to be so worried about it because they are static and long-lived. A problem with this theory has been always that simulations, were never able to reproduce long-lived spiral waves. So they are always transients. They come and go in simulations, and so it's very hard to reproduce them. So this is why for the same time, at the same time appeared another theory, which is more related, so it's an alternative theory from Tumre, Goldrake, and Lindenbell. So the idea is that maybe arms are just initiated, they are seeded from, so they are essentially an amplification by gravity, a local amplification, which is the response of the disk to some internal perturbation. So Tumre mentioned the giant molecular clouds as an idea. So the arms would be like a wakelet, like a wake, which is generated by overdense regions co-rotating within the disk. For example, a giant molecular cloud co-rotating in the disk, or any open cluster, any overdense region, any dishomogeneities in the disk massive enough can generate a wake, and then the wakelet will be amplified by the self-gravity of the disk. By the fact that stars in the disk, they feel the gravity with the other stars. They communicate, they're linked together by gravity, and so they can amplify the arms. That's the classical picture. It's a linear theory. So what I'm showing you, well, first let me maybe make a sketch what this swing amplification is. So this theory tells you that if you have stars in the disk drifting in the flows, there are essentially three ingredients that allow you to form spiral arms. So you need to have, the disk is differentially rotating. There is a shear in the disk. So there is a shear, there is a shearing flow, and stars individually, they are orbiting in the stellar disk on circular orbits. They're not perfectly on circular orbits. They have some random motion in their circular orbits. So they have some little shakes in their motions, which is actually, some epicycle motion associated to them. So if we have stars, which are drifting in the flows, well, it's interesting because by the presence of a giant molecular cloud, so every time you have an overdense region, this giant molecular cloud will exert some force on the stars or individual stars. So stars will get excited in their epicycle motions, in their random motions. So, and because there is, and actually that's a very interesting part of the theory, because there is a match between the shearing flow, so the direction of the shear, and the retrograde direction of the stars in their epicycle motion, there is a resonance. This resonance, will form a wakelet around the giant molecular cloud, and then because of the self-gravity, the wakelet will be amplified and forming the spiral arms. So I was very intrigued by this theory. That's why it's called actually swing amplification, because you have this pattern of stars swinging inwards and outwards because of the presence of the giant molecular cloud. So the leading arm will become, because of the presence of the shear and the differentially rotating disk, will become like a trailing arm and forming the arms. So it's very intriguing because, well, first of all, simulations were able, since 20 years already, to some way to form arms. They are, they are transient, so they are never long-lived. But of course, in this theory, it's interesting because you need a continuous source of perturbation. If they are transient, they come and go. You need something that continuously perturbs them. And so, it could be maybe giant molecular clouds. We know they form all the time until there is gas into the galaxy. But it could be also, maybe these satellites which are predicted from the lambda CDM, and they can maybe, be the source of perturbation of spiral arms.
What's the? I mean, why giant molecular clouds? Why can't a bunch of small molecular clouds do it? Like, what sets the scale which matters? In
principle, right. This is a very good question. I don't have time to show you all the work I've done, but I can show you that. So it doesn't really matter how massive it is. It needs to be an overdense region. Now, if it's very massive, like a giant molecular cloud, it will trigger the process quicker. So the time of the response of the disk to the internal perturbation will be quick. If you reduce the mass of the perturber and you go, down, for example, you go to lower and lower mass, it will take longer time. But let me show you some movies that go in that direction. So just to tell you quickly, the minimum mass you need in a Hubble time to trigger the response in forming arms is 10 to the 4 solar masses. I would say it's a kind of an open cluster, right?
So then that way, if it's the second the dark and visible satellites, then there would be some way to use the number of spiral arms or the kind of structure of spiral arms as a way to constrain.
That's a good question. I will get to that. Actually, I would say no, but I will show you why that's not the case. Okay, so things I'm addressing. So I will show you with using simulations. And why simulations? Because these days, finally, computational power allow us to make some tests on the theories. So, dynamics of spiral arms stopped almost 20 years ago because people were unable to test the theory, neither with the observations at the time, and neither, with theory. We were not able, to test the simulations using simulations. But these days we can, and even, with the upcoming Gaia and the service that we have, we can actually make predictions and looking at and testing the simulation. So I will show you that spiral arms I do not believe are long-lived as the Lee and Shu theory, but my simulations will show you that they are actually statistically long-lived. They are not neither transients, so they don't come and go, but they are statistically long-lived. I will show you, because I'm able to generate now spiral arms and I might know something about their nature. What is interesting is to look at which is the efficiency of radial migration due to the presence of the spiral arms, these non-asymmetric features in the disk. Also, let me show you something I've just published recently, which is the disk response to the bombardment of dark satellites. For example, Sagittarius punched the disk, which is visible, but also we are expecting 500, 1,000 of very small satellites punching the disk. What's the role in forming the features in our galaxy? And how can we test these theoretical predictions with ongoing surveys? Methodology. So I'm using embodied simulations. So the way I set up my simulations, the simulations are set up in isolation. They are not cosmological, and I have a reason for that. So I really want to see each ingredient. What does it play? What is the role of each ingredient in my simulations? I want to control them. So I really go to very high resolution. So I think up to now I have the highest resolution simulations for this kind of work on dynamics. So the disks are embedded in a dark halo. So I choose the mass of the halo, I choose the distribution of the mass in dark matter of the halo, and then I set up a disk which is an exponential disk, as the observations would suggest. And then disks, this is important, they are stable since the initial time. So they always have a stability parameter, the Q parameter larger than 1. So they don't get unstable, so we don't get features because of instability. Very quickly, let me tell you which are the limitations you have with simulations. So once we adopt a methodology, we need to know which are the inaccuracy of our methodology. So if you run simulations with the embody, what you do usually is you choose the mass of your disk, of your halo, and then you discretize the mass in number of particles. Doing this, you introduce fluctuations in the potential. And these fluctuations are noise. So what happens is that this is an example of a low resolution simulation. I fix the number of particles here, and here I go to a much higher resolution, a bit higher resolution of a factor of 10. So you can see that you start forming, as soon as you run the disk in isolation, you start forming spiral arms, you form features. And then if you increase the resolution, the amplitude of your arms tend to become slower. So you can quantify, and that's what I did. You can use the Fourier transform analysis of the stellar disk. The Fourier transform analysis, tells you which modes, so the number of arms which are dominant at each radius. And you can see that the amplitude going from lower to higher resolution decreases for each mode as a square root of the number of particles. That's Poissonian noise. So if you use embodied simulations, you have to be aware that the Poissonian noise introduces features, will excite features in your disk for no physical reason, just noise. Because I know this, I'm using 100 million particles in a stellar disk. And actually for this kind of simulations, very controlled simulations, I use a fixed potential. So I don't use particles for the dark matter halo. But for the disk, yes, because I want to see which features I can create.
Well, why doesn't that bias your results? I mean, there has to be some sort of interaction between the disk and the halo.
Right, but for this work, I'm using disks which are a bit lighter than the Milky Way. Lighter disks do not develop many features. They will only develop the arms. I can control even the number of arms. So they will not develop, for example, a bar. So it doesn't, at that point, I have a clear control in what's going on in my disk. It's not completely realistic. So this is not something you can compare immediately to the data, but it's just to understand. So I want to be able to control the noise. So what I did, you can see here that this is a disk where I pushed up the resolution to 100 million particles in the stellar disk. If you let it running by time, you see that I get these little features via little rings because disks are never completely stable when you run them in simulations. But besides that, I don't generate any arms. Now, this is just the introduction, let's say. So now I believe that my disks, if they do not perturb them, are pretty stable. So they are now forming feature. So what I can do is to test the theory. Now I introduce giant molecular clouds. So I introduced particles which are these are softened particles, so they have the mass of a giant molecular cloud, and they will be introduced co-rotating within the disk. And now let's test the theory. So what the swing amplification theory tells us? It will tell me that, so this is the disk face-on, the stellar disk face-on. These are all the giant molecular clouds introduced in the disk. So they are co-rotating with the disk. That's important. They have to be co-rotating. If they are counter-rotating, the swing amplification, there's no resonance, so there will not be formation of any wakelet. What we should expect here is to see for example, in the polar coordinates around each giant molecular cloud, we should expect to see a wakelet forming and then being amplified and forming spiral arms. Okay, let me show you what we found. So, you can start seeing forming wakelets around the giant molecular cloud, but you can see that after some times, especially between 1.5 and 3 scalents of the disk, which is the typical region between 3 and 12 kiloparsec where you see arms, we don't really see that there's real correlation one-to-one. But if I look at in the outer part of the disk, you see here, so almost 3.5, 4 scalents, then it's true. Then each wakelet is still, related to giant molecular cloud. So what did we learn from these experiments? We learned that actually the response of the disk is more complicated than the swing amplification. So the swing amplification is a linear theory. I'm not surprised that we can capture the swing amplification in the outer parts of the disk because the self-gravity is not very strong. These are, in the outer parts, there's not much self-gravity. So I would say the Tumre theory is actually correct only in the outer parts, where wakelets are not either too much swing amplified. But in the inner parts, between 3 and 12 kiloparsec, it seems that there is a kind of a nonlinear response of the disk, which is more complicated than that. So in order...
Could you do that experiment with just like one?
Sorry, you are always ahead of me. It's 2 slides left after. Yes. Okay, let me just drive your attention on one important thing. So first thing to test, are these long-lived or short-lived? I think, I only read papers from these people, but I talked to Tumre sometimes. So there was a big fuss about how long-lived are the spiral arms. So that was 30 years ago. So according to Tumre, the swing amplification, once we remove the perturbers, they should fade away. Let me show you. Here, it's the same disk. Now we remove the perturbers. They never show away. So actually, it's very interesting. They are some way self-perpetuating, but they are, statistically changing. So they are not long-lived in terms, so locally they are actually moving around. They fluctuate in density, but statistically it's always the same picture. Once they are generated, they just don't fade away. So the first thing we learned is that this nonlinear response, whatever it is, makes the spiral arms actually extremely statistically long-lived. Now let me go to the next point, which is actually your question. I wanted to understand better because we started with 1,000 giant molecular clouds, which are roughly maybe matching the amount that we have in the Milky Way, but then doesn't allow us to understand exactly what is going on. So what I did here is to introduce one massive giant molecular cloud, very massive right now, to trigger the process very quickly, and then see what happens. And so now we are in the rest frame of the perturber, so the disk is still rotating. So you can see here, we're forming now the wakelet around the giant molecular cloud, exactly as the swing amplification would predict. But then, you can start seeing that actually there is an overdense region here around the GMC, but because of the overdense region, mathematically we're expecting also underdense regions. And now, you start seeing here that this part here is becoming too heavy. So it's going to, to collapse some way, to abandon, and here abandon the original wakelet. And you can see here we start forming an overdense region which is not attached to the giant molecular cloud. That's what we call nonlinear response of the disk. This is not captured in the Swin amplification. So this is, you need simulations to see that. Now it's very interesting because I can remove now the giant molecular cloud. That's what I did, like running, the simulation, and you can start seeing what's going on. So the initial giant molecular cloud drives the initial perturbation, drives the initial wakelet. But then we can start forming, you see, other overdense regions, because each overdense regions will attract underdense regions, will attract holes. So we form holes and overdense regions. They are all seeding the disk. So depending how massive is the perturber, how massive is the overdense region, it will, more massive it is, shorter will be to generate this process. But in any case, we will always end up, and if you wait for enough, I will end up exactly with the same number of arms and exactly with the same self-perpetuating picture. So it doesn't matter how many perturbers I introduce.
Is there any worry that the nonlinear response details will depend on the number of particles? Like, how do you know if you have enough particles?
That's a good question. So I think we have seen similar things even if I go to lower resolution. I wasn't able up to now to do higher resolution. That's something that, but right. But what you want here is just to increase the resolution to be able to control your noise and then introduce the perturbation ad hoc. But they are physical some way, because every overdense will attract an underdense. And so they will both these homogeneities into the disk that continuously seeding the arms. And so for this reason, it's also very interesting, to study, why the arms are so long-lived. I mean, they are long-lived just statistically. This is important because you can see that, if you look at, its individual radius or position, they fluctuate, so they are not constant or static. Now, let's maybe go back to the question of Mariam. So how do we regulate also the number of arms? So what I learned up to now is that arms are not transient, as Tumre said, and they are not either long-lived, as Li and Shu said. But how do I regulate the number of arms? So the regulation happens just, it depends only on your structural parameter of a galaxy. If you know the rotation curve, so if you know the models, so if you know which is the contribution in dark matter and the contribution of the disk at each radius, you can regulate the number of arms. So these are simulations that I have done. So this is always the same halo, roughly Milky Way size. I just increased the mass of the disk from 20% at 2 scalens up to 50% at 2 scalens. And you can see I just regulate the number of arms. And they can even do it analytically. So the Swin amplification works at a certain point until I form the arms. It doesn't work on the properties on the long-term arms, but I know that perturbations, so some waves will be, fluctuations will be amplified to generate the wakelet, to generate the arms. So I can, if I know the rotation curve of my galaxies, if I know the kinematics, I know the epicycle frequency. And if I know the surface density of the disk, actually I can even do it just analytically, predict the number of arms as a function of radius. And this is something that actually agrees very well with my simulations, and this is something can be tested with the SLOAM4 data. So the manga survey is already taking 10,000 galaxies around us. They will have available kinematics, so I think it's possible actually to learn about, not only to have a census, how many arms there are in galaxies, to learn about the distribution of the components, the rotation curve, and learning why they have that number of arms.
How do you define arms in the analytic theory? I mean, because an arm is not...
Okay, mostly, right. So usually you want to use the Fourier transform analysis and see at each radius what is the dominant mode. The dominant mode will tell you, it's this M here, will tell you the number of arms. Unfortunately, it is a bit noisy. So, but at the first approximation, it can work. So you can know, and actually you can even enumerate them. In data, it's also tough because depending on the band you are looking at, depends which stars you are, or depending what you are looking into. So I have a student, so we are developing actually an algorithm to try to detect, given an image, how many arms there are, and then comparing with the data and comparing with the simulations. I think the powerful point here is that you can use dynamics, actually, to know exactly how many arms you are expecting. And it gives you a guidance in place of being completely, blinded.
And when you say that the swing theory, the swing amplification theory is a linear theory, is that linear in what quantity? The surface density perturbation, or?
Well, it gives you the response of the disk. It will tell you that it will tell you only the first order approximation, and then.
First order in what?
So it gives you that. It tells you that the solution are density waves. It just doesn't give you maybe enough information on really which are the properties of these density waves. It just tells you that the solution are density waves, but it doesn't give you enough enough power to really make a prediction on those. And so some way simulations might be interesting, and it should be maybe interesting to develop even higher orders in the theory, and just try to see if we can catch up other high order effects that actually in the theory are not there. Now let me show you what the radial migration do now to the presence of the spiral arms. So we have used here 3 different models for galaxies. So I've used here a light disk, which I know now that will generate multi-arm galaxies, so a lot of arms. I'm using something which is heavier and something which has a rotation curve very similar to the Bovie and Rix, which is actually very flat, if we believe maybe very similar to what the Milky Way should be. And so the reason here is that depending on the amplitude of the arms and the number of arms, the response of the disk might be different, and so eventually stars they can be moved around the disk with different efficiency, depending, maybe the number and maybe the strength of the arms. So these are how they look like. So as you can see, so in these 2 cases, the heavy disk and the Milky Way disk, they develop a bar after some time. So they are, too heavy to be just, also bar stable. So they are bar unstable. So what is the answer? So there are claims in the literature. People believe that radial migration, which is this process for which stars. So stars are orbiting. They are on circular orbits in the stellar disk, but they also. So if by the presence of spiral arms of these non-asymmetric features, they can exchange individually angular momentum and energy with the nearby stars. And this bring them, in moving them on a different radii, being still on circular orbits. So they can move from circular orbits to circular orbits, just exchanging angular momentum and energy by the presence of a bar or of spiral arms. So what is the effect on this on the vertical structure? Some people believe it's possible to form a thick disk or to form, a very hot disk because of this. And so, so this is what we find. So this is how much is so. So this is the the variation. So the migration, how much the stars are migrating from their initial position, initial home radii. So they can migrate. So it's a diffusive process. They can migrate inwards, outwards, or outwards in. So they can migrate both places. So the first thing we notice is that. Okay, you can see the one, for example, if I take a star at initially at 6 kiloparsec, that migrated for 50% outwards or inwards, it's always colder in its vertical height. So migration do not actually heat up the stars.
Sorry, the y-axis is a fractional. It's not kiloparsecs.
No, it's a fraction.
Okay.
Right, it's the fraction. A fraction of migration, this would tell you, because it's positive outwards, this will tell you from inwards, so from outwards in or from inwards out.
Okay.
So first things to notice is, even the ones that, they move a lot by migration, and they are still from circular orbits to circular orbits, they are cold, very, very cold. So the extreme migrators are stars that are on the mid-plane. And this makes kind of a sense because, they are the ones that feel, the response of this exertion of torques by arms. So we never see really that they can really get to form the heating of the disk. Now, if we do it as a function of the final radius, where they are today, so as compared to the location of the in situ stars today, the ones that's true. I mean, the very light disks will still right. So even if they migrate outwards, or especially if they migrate in, they're always the coldest. If we go to more massive disks where a bar has some role, then they can be heated up, but they are heated up no more than 10% than the local stars. So and a bar is can heat a lot the stars. So they are not neither on circular orbits anymore once they are heated up so much. So because of this, actually, I do not believe that migration has an important role in changing the properties of the disk in terms of structure of the disk. But it has a role, of course, for chemistry, because it mixes up the chemistry around in the disk. And I think what is more interesting about is that it has, first there's another claim actually. People are looking at now in apogee, they are finding that there are flares, flares in the stellar disk, flares of stars, and these are the data from Jobovi. These color data here are in different beams of metallicity. So these flares of stars, because they have a certain height, stellar height, that is different from their initial one. People could believe that radial migration could be responsible for this. Let me show you what we find. Whatever the model we take, whatever the efficiency of migration we take, we can only reproduce. So the stars that are migrating from outwards in, because they are the coldest stars in terms of the scale height, they are compressed, we believe. Because they are compressed, you can reproduce this part of the data. But the ones that are moving from inside out, they are going out by migration in the other parts of the disk, they never change much their height. They're always very cold, as we find before. So they never match exactly the data.
Sorry, just point to me again, which is the data and which is the model?
So the data are the colored bands, and this is what will come from the prediction of migration for different models of disk, because each disk has a different efficiency. So I think the compression of stars that are migrating from outwards in, because they are compressed, because in our models we see they are the coldest. The extreme migrators are always very cold stars in terms of kinematics. They don't, they get compressed. So I think they can reproduce this part. But the ones that are migrating inwards outwards, which are the ones that people believe can form, flares or by migration, they don't match the data because they're still cold. They are not very hot neither, kinematically.
How much does that depend on? This depends on exactly what the mass profile on the outer disk is, right?
Right. That's a good question. But given just as the distribution, given an exponential profile, the same for everyone, we are never able just by migration, because the powerful part of these simulations is that you can only test migration here, so you don't have other components. And given even the fact that I have a different efficiency, I never really match up exactly the data. And I can show you. So let me show you maybe. So I will tell you about flares when we talk about the satellites. Let me show you why, radial migration is important. It is a process happening. I just do not believe that it has such a great importance for the vertical structure of the disk. So I think this is actually something very interesting that's coming up with data now, and I think theory, it needs to be modeled with theory. So we know that locally there are associations of stars in the UV plot, so in the velocity space. And there is a local structure. This comes from Hipparchus, 20 years ago. And people found that the local supercluster of stars locally, within a few hundred parsec of our sun, really local result. People always thought that it was these associations were coming from an initial giant molecular cloud formation, so all the stars might have formed together. But when people had the parallaxes and some information from Hipparchus and distances of stars in the nearby, they found they could even get out the ages. They found that stars in this local supercluster don't have the same age. And so it's still debated if they have the same chemistry eventually. So they might not have formed in the same giant molecular cloud. And this is extremely interesting these days because Gaia, first of all, will allow us to find many more associations than only not the ones in 100 parsec found up now. I mean, there's a wonderful work from JWST actually about these associations of stars. They're called moving groups. But we can find with Gaia, probably many associations, many inhomogeneities inside the disk. And what's interesting is that we would be able even to maybe discern the ages from Gaia. So what is important from a dynamicity now, and we need a theory for, is that if they don't have the same age and not necessarily the same chemistry, some of these stars might have been interloper there, just put there by radial migration, for example. So we need to account for, spiral arms. What do they do to the stars locally, and can we form this kind of associations? And I think also it has some interesting implications, for a lot of the properties that we want to know about the local rotation and our sun motion, actually. So this is, I think, the frontier, because it wasn't possible today, up to today. So let me show you the final part. So let me show you now, I think I showed you what giant molecular clouds could do to the disk, what the spiral arms do to, to dynamical effects for, for stars in the disk. Let me now show you what satellites do to the disk. So this is, what I've done here is I extracted satellites with mass and size from the lambda CDM model, and then I injected them in the stellar disk that I do have. So let me show you what we get. First of all, what we want to show, what we want to study here. Well, I'm interested in the vertical structure. So the problem here is, if you have one satellite or many satellites punching the disk, you want to study how the orbital energy of the satellite is deposited in the vertical energy of the stellar disk. And so, of course, you can do it analytically. So you can just use the impulse approximation. That's what people have done a lot of time. And then, stars which are in the midplane can oscillate, due to, they fill in oscillations because, they oscillate actually with a certain frequency given the potential of the Milky Way. And then what you can study is you can use the classical Spitzer equation. I've studied a lot also the impulse approximation. You can look at, which is the vertical, which is the variation of energy on the Z component and the vertical line that will depend on the mass of the satellite. It will depend on the impact parameter. When the impact happens, it will depend on the relative velocity between the satellite, which is punching actually the disk. So just, you can consider this alpha parameter, which is a combination of all these quantities that matters into the deposit of the energy. So not all the stars will gain energy when a satellite passes through, but only the stars that resonate. They are again on resonance, and the resonance is broad. So that's the kind of resonance that we are actually dealing with. So the resonance is actually broad. It depends, it will be maximal only when this parameter is 1. That means that the stars that have the maximum energy transfer are the ones that have the vertical frequency. They oscillate vertically as they oscillate, in plane, in the vertical frequency and the horizontal frequency. So some limitations, of course, if a satellite is too fast, there's not much deposit of energy because the energy will scale like 1 over v squared. And if it's too slow, you can see here, too low velocity, then it's like an adiabatic response of the disk, so there's not much deposit of energy. So simulations actually are more important than just using the impulse approximation. The reason is that the impulse approximation from the formulas you have seen tells you about resonances, but it doesn't capture modes inside, collective modes, like bending waves or any modes that is inside the disk. So let me show you, if we do the same kind of simulations with 100 million particles, now we even introduce a halo, with particles. So what we can get here is, so first look at the features. So the features look like actually rings. So in the in-plane, in the face-on disk, the stellar disk looks like rings. And if we look at a John, we start seeing oscillations of the disk up and down.
just one bombardment or one?
So this is a bombardment with all the satellites.
So, and it is continuous. I mean, you have to have.
Yeah. I can let it running for 3-4 gigayears. So we see, kind of a bending waves here, and we see this kind of features. And now, of course, we can have some guidance from theory about the these long wavelengths. So if we use, the Tumre dispersion relation, actually we can learn that given the halo that we put it up with dark matter and the kind of disk, the wavelengths should have a very long, actually they're very long. So what we are expecting now is to see that these wavelengths, because they have long wavelengths, they propagate in the other parts of the disk. And so once they are damped, they should actually heat up the disk. And because they are damping in the other parts eventually, we see a lot of flares, as you could see already from the simulation. So indeed, I quantified this. So if you have many satellites, you can see that the disk by time will be heated. And you can even look at the rate of heating of the disk, and you can form a lot of flares. But let me show you also, so it is true, flares could be, so I haven't really compared to the data yet, but they could be formed, more likely by satellites punching the disk. Not each satellite, so I didn't have time to show you the entire work, but if you only consider little satellites punching the disk, they actually don't do anything to the disk. If you go to the same size or mass like a globular cluster, they don't do anything. But if you have something like Sagittarius, or at least a few massive objects, 10 to the 9, for example, solar masses, then, or even many with 10 to the 8, which is what you expect, then you can get a result like this. Now, one thing that actually I found very interesting in this kind of simulations is that locally, so if you look at here now, so this kind of movie, so this is the in-place, so this is the surface density of the disk, and this is the scale height of the disk. So let me show you, if you can see here, in the underdense region, stars tend to go to have a vertical excursion. So they tend to flare in the underdense region. Now, our Milky Way is our sun is in the Milky Way in an underdense region. We are not on the arms. We are in a kind of underdense region. What my simulations do predict is that there are not many stars. It's an underdense, okay? But those stars have a vertical excursion. So they go, they have a flare on the scale height of the disk. Why this is so interesting? Well, it's interesting because we know that there's another big problem right now, which was initially initiated by Oort, which is the local density of the disk, the estimate of the local density. And people, it's also important and interesting because there always been a claim that there might be contribution or not of the dark matter to the local disk. And we still, people do not believe that there is dark matter there, which I think it's a fair result. But let me show you this. I mean, if this is correct, if my simulations are correct, it will tell you that locally stars can oscillate with a different scale height. This means that we are in a region where maybe we are inside a local flare. This local flare makes the disk not in equilibrium vertically. And every time we derive the local density of the disk, even observationally, we always assume the Jeans equation. We also assume equilibrium. So I think, there are differences. So what I can see here is that there are,
The constraint is a comparison of the velocities with the scale height, right?
Right.
So are you saying that in these, as the scale height's varying, the velocity is not varying in the way you would expect in equilibrium?
They don't vary in equilibrium as well. And then, so nothing, they're not, there is a perturbation in the velocity as well.
Right, but it brings you off of the relation you would expect for an equilibrium disk, you mean?
Right.
Okay.
So what I'm telling you is that that could be interesting because there was one day a problem which is called the Oort limit, which was a discrepancy between the observed local density of the disk and what you infer if you use the Jeans equation, if you just make your disk at equilibrium. and if you assume that the potential is static. Once we have simulations, we see that the potential is not static because we have non-axisymmetric features, and we have also, eventually a completely, a time where the disk locally goes out of equilibrium. So my question is, what would be interesting now is to understand what can we learn about the local density of the disk. So how can we even look at again the data to re-look at it, it's actually which is the contribution of dark matter, which is the contribution of the local density in the disk. And this is interesting because some people do believe that there is a dark disk, so disk of dark matter. Some simulations have shown it, some simulations didn't show it, and these have some interesting implication, for direct detection or annihilation processes. So I think from the dynamical point of view, we can actually address this calculation, given the fact that we are simulating something similar to the local neighborhood.
That's a good question. So when people do these kinds of dark matter, we had talks about that, so dark matter indirect detections and so forth, what kind of densities do they assume? Is it the 70, the number you put earlier?
I do not, honestly, I don't believe it. I don't believe they use that number. The number comes, actually put I put the last number from Joe Bovy and Scott Tremaine. But some people, have a different question about that, and they have a different answer. So it's still a debated value. My point is that maybe, it would be interesting just to redo even the analysis with the data. And, I cannot do this. Okay, let me show you now what are the future directions I'm going on these projects. Right, so, okay, just to mention also another thing, there are also observations locally of an asymmetry in the number of density above and below the disk, which has been found from other surveys like RAVE, so other surveys, SIGWE. And it would be interesting to see if Gaia refines the same, but that would be actually something also related to this local flare. So you see in an asymmetric number of density of stars, but not because there are necessary bending waves yet. It's just a restoring force in the disk, because these are an underdense region. And it would be actually driven by Sagittarius eventually, because Sagittarius punched the disk a giga-year ago. Now, future directions. So what I'm doing now is, I used the giant molecular clouds to perturb the disk to form spiral arms, but I showed you also that I actually form these overdense regions. And by gravity, it would be interesting to see if once we add gas to these simulations, we can reform the giant molecular clouds. So that could be an interesting way to connect the formation of arms to what the arms bring to or lead to. Also, I'm interested, I think the velocity ellipsoid is still very unknown from simulations, but the data that are coming up will tell us a lot about the velocity ellipsoid in the stellar disk.
What's the velocity ellipsoid?
So we want to know, the ratio between, for example, the velocity dispersion, on all the components, which is the phase space of the stars. And these things, there's not much work has been done up to now, but with the upcoming Gaia, maybe, the data will be better, but even simulations can make predictions about this. So it hasn't been done right now. But, and I think the challenge to me is actually really looking at not the inner parts of the disk. Everyone looks at the formation of a bar, and what a bar can do, or spiral arms just in the inner parts. But the challenge is actually in the outer parts of the disk, because we have flares happening there, so they are much more sensitive to any kind of perturbation from satellites, from Sagittarius. Also, there's not much exploration about the other parts of the disk. For example, for moving groups, for these associations of stars that might have formed in different regions, not necessarily in the same giant molecular cloud, the outer disk will tell us, or at least a 10 kiloparsec, let's say, I'm not saying outer 15 kiloparsec, but a 10 kiloparsec, for example, will tell us that, these stars take longer to move, to rotate into the disk. And so it will be easier to find this kind of streams, because these are streams of stars with different ages. And the idea, I think that's what I found very interesting. I think David Ogg is working in trying to find observationally maybe some of these groups. So I think the challenge would be to search for them, so search for associations of stars that are streams, inhomogeneities inside the disk, and actually trying to explain them. So what I'm doing right now is a simulation of the kind I've actually showed you today with giant molecular clouds, just a stellar disk. And what I'm doing is, once I generated the arms, I'm actually looking at into one open cluster, a kind of initial cluster of stars, and see how it dissolves in different parts of the disk, and how the migration can affect that kind of open cluster once it dissolves. Because then I can learn, by migration, for example, how can I reproduce some of the features actually that Gaia is going probably to highlight in the next few years. I think I stop here and I take questions.
More questions?
One general question. You mentioned the spiral model of the 1960s, and then the work of Bertin et al. That was much later. But then, so what did Bertin et al. Do? Because I didn't see what did
I think
which of the families did it belong to?
I think they belong to Li and Xu. So it's the same kind of theory. They developed a bit more, but it was the same idea. So still long-lived and not changing by time, and right. So.
Which is not what you see in this.
No, which is not what I started with, because simulations never show that these are, static. They just change continuously. So it's impossible to test the theory with, at least now with simulations. And they also predict, that the path and speed of these waves would be with a constant velocity. And now these days we have data to start comparing. And I don't think the galaxies that have been studied actually go in that direction. So we know that there are not static density waves.
Yes, if I remember correctly, in the abstract talk, it is mentioned that numerical simulations predict a much larger number of satellite galaxies than observed. Is that a serious problem?
Well, yes, okay. Simulations do predict a lot of satellites that should be visible and some invisible because they are so small that they probably don't have stars. Now, this was a huge problem because maybe 10, 15 years ago, because people, were predicting in simulations 500 satellites within 500 kiloparsec, and then 15 years ago, we didn't have many observed dwarf galaxies around the Milky Way. There were 11. I think these days, thanks to the slow one, actually, and not only to the slow one, this year also thanks to the Dark Energy Survey, we found many more ultra-faint dwarf galaxies. But they are not 500 up to now. I think they are in total 30, around 30. So there's still a factor of discrepancy. But the fact that there are, almost every few months we find new ultra-faint dwarf, the very faint ones, makes promising that maybe it's not a huge problem of the theory. So they are there, probably. They are just very hard to see because they are so faint. And I would say that, dwarf galaxies are very interesting these days because, they challenge, they are a challenge for the lambda CDM. But I wouldn't say that that was called the missing satellite problem. I don't think it's actually a huge problem anymore. And the new surveys will tell us more, they probably discover more and more.
So that's a follow-up question. So assuming that the flares that you see, that people see in the data that cannot be explained by the first part of your talk, which is
the migration.
Yeah. If that were due to satellites, these kind of very low luminosity, low mass satellites, but not too low mass, punching through, would the data be consistent with the number that is required by lambda CDM, like let's say 500 with a certain kind of radial pattern or radial distribution?
Okay.
Have you looked into that? Or?
I haven't looked into that, but so I cannot give you a quantitative answer. What I can tell you is the ultra faint they might do something if many of them punches, if they have a mass of 10 to the 8 solar masses. Below that mass, they don't do much to the disk. There's no flare in that case. Everything from 10 to the 8 and higher mass can actually create this response of the disk. Now, it's not true that all the dwarf or ultra-faint dwarf pass through the disk. I think actually I also done some work on this. I would say that only 10 to 15% of the satellites predicted in lambda CDM pass through the disk. So it depends also on the orbits. But you don't neither need ultra-faint dwarfs. I think Sagittarius is actually enough. Sagittarius is massive. Is one of the brightest dwarf galaxy. It's punching, the disk. Probably punched already a giga years ago. So it's passing, probably in several passages. So it seems enough to create this kind of wobbling or flares. Now, I think it's interesting to make a clear prediction, really a prediction with the data right now, which we haven't done yet, but on the way.
So perhaps I'm overly influenced by astronomy picture of the day, but you didn't really show any simulations of disk galaxies that had spiral structure that I would really, compare to canonical grand design spiral galaxies. And the challenge is to try and get these excitations of low order modes or things that have low numbers of spiral arms. So how do we make grand design spirals?
Oh, we make what?
Grand design spirals.
Grand design. Okay. Okay. I would say that the idea of Lee and Xu, like static waves, like a global ideas, of global patterns, might not be correct. But one way to do them could be, for example, a satellite, so a tidal interaction could be, because we know that many of the grand design they have a particular shape in their arms. So they could actually, they're kind of a roundish. M51 is one example, and they satellites do generate more than, not really spiral arms as they generate a kind of very roundish spiral arms in terms of they're like offset rings. So every time we see something like an offset rings or something that has a shape that goes like a ring or things like that, it's probably by satellites. And our galaxy do have a ring. So we know that there is a ring also in our galaxy. That might be, again, the remnant from Sagittarius. For the kind of spirals that comes from the theory like the swing amplification or nonlinear version of the swing amplification, arms tend to be, they have a different shape. They tend to be more segments. So every time we see maybe arms more like a segment, they might be more internal processes. But galaxies could have also both processes happening. We have Sagittarius, but we also have giant molecular clouds inside our disk. So it could be a combination of both things. So I would say that the number of arms, I think, can be predicted by dynamics straightforwardly. So we can know, if you tell me the kinematics of a galaxy, I can tell you how many arms it has, even as a function of a radius. And for the different arms that we see, or the different shapes, or the grand design, for example, then it depends a lot also, on the shape of the arms, and I think maybe a combination, of satellites plus, plus internal processes can still be interesting. What I do not believe is the classical theory. I mean, just this grand design formed by static density waves. I don't think that's actually correct.
Do you expect the gas to play any role for the Milky Way? It's a substantial fraction of the mass, but not dominant. But for other galaxies, even the Milky Way size, it's it can be half of the disk mass.
So for which problem? Spiral structure, you mean, or?
Yeah, for spiral structure.
Okay, spiral structure. Because I believe the swing amplification, some version of it, it's a dynamical response by gravity. So in first approximation, it should be the same for gas and stars. Indeed, there is a picture, I don't have it actually here, but on the Binet remain, the response of the disk for a gaseous disk or a stellar disk by Tumre. There's this classical picture that shows you that the amplification is very similar for gas and stars. This is why I think it's good theoretically to start.
Turn off cooling, I guess.
Right. So in first approximation, the response, so the number of arms, it shouldn't change. What you see in gaseous disks is that disks are thinner, so they're colder some way. So you have a sharper response. So you see better defined arms eventually. But I think that in terms of response, it should be very similar. Then, of course, if you consider shocks or all the physics, gas is dissipative, then you can end up with very detailed prediction, maybe to make a comparison with data. But in terms of the response, I don't expect to have a different one. It's also easy to see if you go back to these theories from the 60s. Goldreich and Lindenbell did the swing amplification for a gaseous disk. And Julian and Tumren did it for a stellar disk, and they got a very similar result. So, but it would be good to have both in the simulation. That's also one of the goals, to make something more realistic.
So, maybe 10 to the 8 was an interesting number of particles for your disk. Have you thought about doing not ultra-faint dwarfs, but just regular dwarfs which have 10 to the 8 stars? Is that?
Yeah, that's one of the things.
It's not exactly the same because you presumably can't get the sub-parsec resolution, but.
Yes, so this is one of the things that I think should be done. Yes, it's on the list of things that I would like to do. Also because once you introduce, visible dwarf, you can study streams, for example. So you can use simulations like this one, and looking at streams of stars and studying. There's not only the response of the disk, but then you can also see, given the potential that you introduce in your galaxy, maybe how the streams, the shape of the streams for galaxies like.
This is dropping in a dwarf to
right.
something bigger. I see. Okay.
So that could be that could be more broad. Here I was interested first on the response of the disk, but of course if you make things more realistic or put stellar structure in a dwarf, then you can see better even how these stars are stripped.